Alright, hi chemistry class. This is your lesson for day 62. It's May 26th, and we are beginning the 5th week of distance learning. This is another short week, only 2 weeks to go. So we're going to start a subject called gas laws, and this just talks about the principles of gases. Alright, so we talked about gases last week when we talked about intermolecular forces. So remember that all molecules have a battle between intermolecular forces that want to attract them together and kinetic energy, which gives them enough energy to pull apart from each other. So if kinetic energy overwhelms the Coulombic attractions between molecules, in this case water molecules, then the molecules separate and exist as gas or as vapor. So the study of gas laws treats atoms, molecules, and ions in gas state as though they were little balls. In other words, we don't care about protons, neutrons, and electrons. Since the gas can be either an atom, molecule, or an ion, we just use the genetic term particle. We just call it a particle rather than saying atom, molecule, or ion. So we're going to just treat O2, even though we know it has two oxygen atoms covalently bonded together by a double bond. We've talked about that. We don't care about all that. We just care about, in this case, when talking about gases, is that these oxygen molecules are going to be separated, and so they're going to be flying around kind of randomly like this. So gas particles, though, don't randomly change direction, as you saw in the last slide, or as you see in this slide. You must imagine that these particles are changing direction because they are encountering other particles that you can't see, or they're hitting the sides of a container. So this gives gas particles their apparent random motion. So gases can take part in chemical reactions. For example, the chemical reaction we've seen quite a bit in this class is two hydrogen molecules in gas state and one oxygen molecule in gas state will give you two water molecules in gas or could be liquid. The water can be produced from hydrogen and oxygen gas. So gases can be involved in chemical reactions, but we're not interested in that. This is more of the physics of molecules. It's how do they behave like little balls. When you throw a ball through the air or when you bounce a ball off the wall, that's more a topic of physics than chemistry. We're not interested in them combining in chemical reactions. So in this unit, we are only interested in how gas particles behave due to four external factors. The first is the pressure of the atmosphere, and therefore the pressure of the gas itself. Second is the temperature of the atmosphere. The third is the volume of the container, how big the container is. And fourth is the number of particles, which we express in moles. So let's start with pressure. We can think of pressure as how many times the particles hit the side of the container. That's a good way to think about it. So if you want to know whether pressure goes up or goes down in a certain situation, ask yourself, are the particles inside that balloon or that glass jar, are they going to hit the sides of the container more often? That would be an increase in pressure, or less often, that would be a decrease in pressure. Volume is the amount of space that the container occupies. So in some cases the volume could change, such as in the case of a balloon where it can inflate or deflate, get bigger or smaller. Or in other cases the volume can be fixed, such as a glass jar where the volume can't get bigger or smaller. Temperature. Temperature is the average kinetic energy of gas particles. This is a little less clear what that means, so I'm going to give you some examples. Kinetic energy is given by the formula, and this is one you had back in physics class. Kinetic energy equals 1/2 the mass times the velocity of the particle squared. M is mass, V is velocity. So by increasing the temperature, we increase the average kinetic energy. That's what temperature is. It's the average kinetic energy. We increase the average kinetic energy of the particles. Since the mass, M in that equation up above, has to stay the same, that means if you increase KE on the left side of the equation, you have to be increasing V or velocity on the right side of the equation. So what that means is you can think of increasing temperature as increasing the speed of the gas particles. Alright, let's say we have particles of two different masses. So how is that affected by temperature? How does temperature deal with two different masses in a container at the same temperature. So this means they'll have the same kinetic energy, the same Ke, because that's what temperature is. So let's assume the following. Let's just do a thought experiment. Let's just pick out some numbers here. Assuming that you have a particle A and that has a mass of 2 atomic mass units, and then a particle B and that has a mass of 8 atomic mass units. So particle B is 4 times more massive than particle A. And let's say you have a certain temperature, and that certain temperature gives both of those, doesn't matter how big they are, the same kinetic energy. And let's just pick a number. Let's say that's 16 joules. So both particles have the same kinetic energy of 16 joules. So what we can then do is compute the velocity of each particle. So simply plugging the numbers into the formula Ke equals 1/2 mv squared, for particle A, you'd have 16 equals 1/2 times 2, the mass, equals the velocity of A squared. And if you solve for A, you get a velocity of 4. Now for particle B, kinetic energy is 16 times 1/2, the mass is 8, times the velocity of B squared. If you solve for B, you get a velocity of 2. So you'll notice that the smaller particle, the lighter particle, is twice as fast as the heavier particle, a velocity of 4 versus a velocity of 2. So the 2 AMU particle moves 2 times faster than the 8 atomic mass unit particle. The 2 atomic mass unit particle moves 2 times faster than the 8 atomic mass unit particle. This leads to the following relationship for 2 gas particles, and that's called Graham's law of effusion. Fusion is basically how fast molecules move, but we'll give it a specific definition later in the week. So the speed of the lighter particle compared to the heavier is given by the equation the mass of the heavier over the mass of the lighter, and then you take the square root of that number. So in our example, the heavier particle was 8, the lighter particle was 2. You divide that, you get 4, and you take the square root of 4, you get 2. So you'll see that this equation gives you that the smaller particle is twice as fast as the heavier particle. It doesn't give you the specific velocity it's going in meters per second or anything. It just tells you how much faster it is based on its mass. All right, so temperature is the average kinetic energy of the molecules. This translates to meaning that for a specific type of particle, in this case a hydrogen molecule, the higher temperature increases the speed of the molecule. So you have this one at normal room temperature, and then if you take that same particle and turn up the heat underneath it, it goes faster. So just think of temperature as increasing the speed of particles, molecules, atoms, whatever you have in there. Okay, there's one major factor that relates the 4 variables of gases, and this is really the only major equation in studying gas laws. It's called the ideal gas law, and it says PV, pressure times volume, equals nRT, number of moles, times R, the gas constant, times temperature. So P, V, T, and N have already been previously defined. That's pressure, volume, temperature, and number of moles, basically how many particles you have in the container. R is called the ideal gas constant, and it is 0.0821 liter atmospheres over moles Kelvin. So the L is for liters, that's a unit of volume. ATM is atmospheres, that's a unit of pressure. MOL is for moles, that's what the N in the equation stands for. It's number of particles or number of moles. And K is the temperature in Kelvin. The purpose of this constant is that it cancels the units of measurement, so only the units in the final answer appear. So let's say we were trying to find pressure in atmospheres, and you took that equation and you put in volume, number of moles, and temperature. It would cancel out all the units so that the only unit that appeared in the final answer for pressure is atmospheres. What it is it's like 4 different conversion factors all bundled into one single number. You remember how we used conversion factors in stoichiometry last week? Well, if you took 4 conversion factors for pressure, volume, number of moles, and temperature and wadded them all up into one number, that's what you would get. One of the things that gas constant tells you is when you're working in a problem, you have to be sure that you're using the proper units. For example, if you're given the temperature in centigrade, that number's no good. You've got to convert it to Kelvin by adding 273 to it. And so what this tells you is what units you have to be using. Your volume has to be in liters, not milliliters. Your pressure has to be in atmospheres, not one of the other measures such as pascals, which we haven't talked about that, but it can't be in that. moles is moles, and Kelvin, temperature has to be in Kelvin, not in centigrade. Okay, so using the ideal gas law, we can see how any two variables relate to each other. So an ideal gas, what is that? It's a gas where the gas particles don't interfere with each other. In addition, intermolecular forces between the particles don't exist, so the particles don't want to stick together. So they have enough energy, in other words, so that they'll overcome the dipole-dipole, the hydrogen bond forces, the London dispersion forces, any of those forces that would attract them together. They have enough energy that those forces don't come into a factor. So just think of them like billiard balls. When you see somebody playing pool and two billiard balls, they just click off of each other and move apart right away. That's what these particles are doing. They don't stick together, they don't slow each other down, they just bounce off each other and keep going. Okay, so let's just isolate two of these variables at a time. So what happens to pressure when volume is increased? So in other words, we're increasing the volume, and if you look at the equation, this is just basic math. If you want N, R, and T, anything that's in red is remaining constant. So if you want N, R, and T to stay the same, and you increase V on the left side, then that means you have to decrease P on the left side, so that they offset each other so that N, R, and T stay the same. So if N, R, and T remain constant, then as V increases, P decreases because the particles hit the sides fewer times. So let's see. So on the particle on the left, these particles both have the same temperature. So that means they're going to be moving at the same speed. So if I now start this particle over on the right, it's moving the same speed as the particle on the left. But you'll notice the particle on the left is hitting this container sides more times. The particle on the right, after we expanded the volume, we made the volume get bigger, the volume on the right is bigger, then that means the particle on the right is hitting fewer times per second. So that means the pressure has gone down. Remember, we define pressure as how many times does the particle hit the sides of the container. And as you make the volume bigger, the particle has a farther distance to travel, so it's going to hit the sides of the container fewer times. So as volume goes up, pressure goes down. This relationship between pressure and volume is called Boyle's law. All right, so what happens, now we're going to compare pressure and temperature. So what happens to pressure when temperature is increased, assuming everything else remains constant? Well, if you just look at the equation, you'll see that as T goes up, if you want the equation to remain in balance, then P on the other side of the equal sign has to also go up. So if N, R, and V remain constant, then as T increases, that is, you put fire underneath that container, all of a sudden that particle is going to start going a lot faster. So as temperature goes up, the particle moves faster, it hits the sides of the container more often, and that means the pressure has gone up as well. The relationship between pressure and temperature is called Gay-Lussac's law. Now the relationship between volume and temperature. So what we're saying is, what happens to volume when temperature is increased? So if temperature goes up and volume on the other side also has to go up if the equation is going to remain in balance. So this is the hot air balloon equation. So if N, R, and P remain constant, then as T increases, V increases. For a particle to hit the sides the same number of times, that is to keep the pressure constant, because in this equation pressure is staying constant, while the molecule moves faster, that is higher temperature, the volume must get bigger. So each of these particles is hitting the sides of the container about 2 times per second. If you were to time it, they're both hitting about 2 times per second. But since the one on the right is going faster, in order for it to be hitting the same number of times as the one on the left, the container has to be bigger, the balloon has to be bigger. And therefore, when you increase temperature, if you want to maintain the pressure as being constant, then you have to increase the volume of the balloon. So this is called Charles' law. Okay, and finally one more, the relationship between moles, number of moles, and pressure. So what happens to pressure when the number of moles is increased? That is to say, you increase the number of particles in the container, but you keep the volume the same and you keep the temperature the same. So the container's a fixed volume and the molecules move at a steady speed. So if PR and V remain constant, then as the number of moles increases, P increases because there are more particles hitting the side. So instead of just having one particle hitting the side, you have two particles hitting the side, and that means they're hitting twice as often. If you put 3 times as many particles in, they'd hit 3 times as often, and that would mean the pressure would triple. So the relationship between pressure and number of moles is called Avogadro's law. Okay, so that takes care of this basic lesson on gas laws and how gases work, how they behave under different conditions of temperature, pressure, and volume, and number of moles. And I have a quick worksheet to work for you to work on, and that'll be your assignment for the day. All right, have a good day. We'll see you tomorrow.